Sorry about the little challenge. So we just head on to what we have for today. I think we spent almost an hour already without doing anything. My name is Ofodime Alfred William. I'm a tech steward. I'm a technical specialist. So a professional design for additive manufacturing and a certified instructor. And of course, we've already met Mr. Tolu, who took some parts of the session yesterday. So I will just move straight to what we have for today, and then see how far we can cover. Please confirm that you could see my screen.
Yes, please.
All right. Okay, so basically we learned a lot about Fusion 360, why we should use it, how it's important, how the interface works, and all of that. And then I promised that we are going to see how we can use Fusion 360 to carry out this product design and product development we have been talking about. And so our case study is a lithium-ion battery charger. So basically, what I will be covering will be on the aspects of the enclosures and some of the considerations. We are going to have another instructor who is going to take us on the aspects of how to actually go about the the electronic components and all of that. So having said that, I'll move straight to some making us get acquainted with some terms. I know they are not out of place. They are terms we hear every day. But sometimes you still have to ask yourself the question: do you actually understand what these terms are? Do you actually know how they affect the product you want to build? We are looking at a case. Probably you're taking something from
Just hold on, please.
Okay.
It's all of them. The rights of the phone up. Let me know now. The light is off. Light. I think we are back now. Oliver, can you hear me?
Yes, please. And how about the screen? Is it still projecting?
Yes, yes. So can you just move back? I think the previous slides so that you guys can get
Okay.
started now.
All right. All right. So as I was saying, we will be looking at the production, how we go about, from the conceptualization to, having an actual product in the market, the thought processes and the well-informed decisions that you have to make as maybe the design engineer, the application engineer, or maybe the technical specialist, or just a designer. Understand? So we are looking at, like I earlier mentioned, is the case study is a lithium ion battery charger. So I'll move straight to the terminologies, which I mentioned earlier before we had a little break. These are terms that you as the designer have to get acquainted with, because they affect everything you do, as with respect to a product you're building. So for instance, you hear of the term product requirement. What does it actually mean? How does it affect what you're working on? How do we clearly have that distinction between maybe product requirements and other terms you've also heard, like product specification, product functionality? They all seem like as if they are saying the same thing, but they actually are not saying the same thing. So the first one we are going to be looking at is a product requirement. So before we go into maybe looking at it from maybe your dictionary kind of explanation, once you hear of product requirement, the first thing that should come to your head is, what is that way that you can define what a product must achieve without necessarily specifying the details? That's the technical details now. So it's just like the when you hear people play around with terms like talk is cheap. You understand? So hello, are we together?
What's the problem? Hello.
Are we together?
So why is this thing like connecting now? See people's network frustrating. But I suffer this one, I suffer this one. Hello, can you guys hear me?
Yes, I can hear you. Can you hear me as well?
Yes, I think the internet disconnected briefly, but it's back now. I did too much. No, it's just this. It's supposed to be better, but so they just do it part by part. Like you don't have desktop computers, so not everybody should plug everything at once. Right? Even though you start 30 minutes to switch, it will still last. Right? Okay, go ahead, guys. Go ahead. Go ahead, please.
All right, thank you so much. So as I was saying, whenever you hear the term product requirement, before you go into those details of literal definition, you should have this kind of thing that you picture. That makes it very easy for you to now do what distinguish between maybe requirements, specification, functionality, and the rest of them. So for product requirements, it's just simply asking you, what's that way you can
just hold on.
Okay.
Hello, funny, just hold on, please. I just wanted to call the attention. The class, I don't like, you guys are not paying attention. Like nobody should be looking at their laptop. Nobody should be looking at their PC. Like, if possible, close your PCs. You don't need it open, please. And what we said yesterday and what you're going to start now is very critical to what we're going to take. We're not going to have more than 20 minutes for this section. But what you're going to do in the next 10 years, 15 years as a product designer, every single thing, if you mix these things and understand these things, whatever you are doing in Fusion is useless. I just want to highlight why it's critically important. If you just want to be a graph drafter who just does something that looks like something, you are fine. But if you really want to get to really produce something meaningful, please close your laptops, just focus on the screen and pay attention. If you don't understand anything, ask him questions. The essence of this section is that you actually participated in this section is how many number of questions you're able to ask. Please and please. Thank you. Before we go ahead.
Thank you, Mr. Felix. Okay, so like I said, how do you specify what a product must achieve without necessarily being specific on the details, as the technical details, of what that product should achieve? That's simply what we mean when you hear a product requirements. All right. So, for instance, someone just comes and tells you, I want you to do this for me, and then I want it to be aesthetically pleasing. It should be durable. Ease of assembly and all of that. Those things are to us, they are just like when you say talk is cheap. You understand? Not as if it cannot be achieved, but those is still what's very open. It can mean a lot of things. You understand? So that's the concept of what's product requirement, and that's mostly how your client is going to come to you. So just because of our time, so I will just quickly guide us through some of the product requirements we have here. So we've pictured when we have what we are about to make, after this session. So having that, holding that in your memory. Now, you now look at some of these requirements and then see how they will tally with that and how we are going to see how we can get them done at the end of the day. So for instance, the enclosure which we are trying to build as a first requirement now must provide a robust protection for the electronic components inside. Of course, we had a glimpse of what it looks like, so you should start picturing what we are talking about. Now, the next one, we said provision for external user interactions. So definitely there are ports around the that device. You understand? So how are you going to make that your design such that there is that ease of something coming from outside and having interaction with something that is inside? Do not forget, your enclosure is more like you are building a house or a cage for something. So you're literally protecting what is inside against what is outside. Don't know if you're getting the point. So now, even with that, trying to protect this against that, there are still cases where you have to still have that link between what is in and what is out. You understand? So that's the part of the provision for external user interaction. So the next one we say it must be portable. Of course, the next one we say the design enclosure should be compactable, a standard printer. So it's also another thing you need to know that after all is said and done, whatever it is you're going to be pushing out there after maybe you've done your design and you've done your validation and everything, the machine itself, which you're going to use, in this case, since we are also looking at design for additive manufacturing, so we are talking 3D printers right now, right? So the machine you're going to use to push your digital data into a physical one also will affect the ability of you having your idea being translated into something that is functional at the end of the day. So the machine capability also has a part to play. And the next one is the provision for natural convection. So these are like things that maybe your client has come to you and like, okay, I want you to do this for me. I want you to have this and so on and so forth. So for instance, we know that the electronic components in there will heat up is like a normal thing, is like a default thing because it's, it's working. You understand? So how are we going to ensure that if maybe we are not using maybe something like, for instance, a fan, which, in this case now will be acting as something that is giving you what is called forced convection. So if we're not having something like a fan inside, which is going to carry out that activity, how do you now make room for maybe other ways of cooling, the what is inside? So in this case now we're talking about what natural convection. All right, so the next one, still part of the requirements, we say it must be simple and it must have a simple and cost-effective locking mechanisms. So there are many things you might want to do as while designing, but you also have to look at these things you're trying to get done on this design. What's the cost implication? Yes, it might look good on the design itself, but you don't want a situation whereby maybe you've done a design and just the bolt, for instance, I don't know if you're getting me, just the bolt is even more expensive than the entire enclosure. It doesn't make sense, especially business-wise. Now you understand, because do not forget we are talking about product development, product design, and everything is all encompassing. So it's not just what you're doing on your laptop, trying to get the design out. You're also looking at the after processes that will come in. All right, so we've looked at the product requirements. Another term that you need to also get, or even if you've known, just to refresh your memory on, is called what's product specification, which you could see on the next slide. So what is specification? So all we are simply saying is this is more like an extract now from your product requirements. So after you've done, oh, you must have this, you should have this, you should do this, and all of that. Now you're going to have to pick those things that have been mentioned and break it down to the point where you know specifically the things that you will be incorporating into your design to achieve that thing that was mentioned as a requirement. That is simply what we are talking about when we say product specification. So it's includes like your dimensions, that's the geometry, size, the materials that will be used, performance criteria, and the rest of that. So on my screen are some of the requirements, specification that has been listed that we are going to also have as part of our consideration when we are working on the actual design. So we say that the size of the enclosure should not exceed the PCB's dimension by more than 35 millimeter on all sides. Do not forget, if you can recall, we said it should be portable. So it's not going to be a situation where you have the electronic designer has done his part on trying to maybe get the PCB to a certain size. You understand? Because do not also forget that this PCB will also be probably produced. So it's also, we are talking money at the end of the day. So he has done his bit to get this PCB to a certain maybe size. And then you at the other end, who is now maybe handling maybe the design of the enclosure and all of that, you are now kind of trying to make maybe ×2 of the size of the PCB. That does not make design sense. You understand? It could make sense in other perspective, but within the context of what we are talking about, that wouldn't make sense. So we say we might not know exactly, maybe it should just be maybe 3 mm or 4 mm, but we say it should not exceed. So we can work with that. There are other cases where you can also have very specific terms, like it should be 300 by 500. There are cases like that. It's also part of specification we're talking about. So the next one is the material type. So we are looking at using PETG or PLA. Some of us might not be familiar with these materials or these terms. So these are basically, for now, all you need to know, these are basically kinds of filaments. These are kinds of filaments that we use for printing materials out on the 3D printer, and each one of them have unique feature, unique use cases, and everything that comes with it. You understand? So just like in the case where we talked about the enclosure being able to protect what's inside. So we can start with PETG to give us that kind of requirements we are looking for. So the next one we have here on our specification is snap fit design. So this is also a specification, because now we are not just saying it should have maybe something that can allow you to make your assembly to be easy, or maybe something that just cost effective. But now you're being very specific that you're using what is called a snap fit design. And of course, when you look into that, you now see how it works and how it can also be incorporated into your design. So the last one we have here is called IP rating. So this one simply stands for ingress protection, right? So we are looking at these are what standards that we use, especially when we are dealing with enclosures and electronic components. Are we together? So, for instance, you see the like the numbers and then the symbols. Like you have IP, then you have like 3 and 0. So each of those numbers, the 3 has what it stands for, the 0 has what it stands for. So we're also going to all of this when we are doing the actual design of the actual component. But you should know that these are terms. The IP rating now is something that you are going to have to adopt on your design, which will tell the users that, oh, this design is protected from maybe a fluid at so pressure. For instance, a very basic example would be, we all know that there are some phones that if you put inside, maybe you dip it as if when immersed in a fluid, will stay for a while, and then you can still pick it out and nothing happens. Maybe like your iPhones and some of them. And we also know that there are phones out there that before it even lands in the water, it's already as if the water has gotten into it, if you get what I'm trying to say. So all these things are dependent on the kind of ingress protection. That's protecting against something, what's getting into it. So basically the two things that are of interest are usually objects. That's physical objects, like you're protecting maybe someone's hand from getting into something, or maybe needle or things like that. And then the other thing that we also have of interest is fluid. So those are basically the two of them. So having said that, we move straight ahead to our formulated design constraint. So why do we call this a design constraint? Okay, just before we get into this design constraint, let me just show us a bit of one other term that will also affect our thought process before we get back to how we formulated the design constraint. So that would be our product functionality. So what do we mean when we say product functionality? So we are simply talking about the capabilities of the product, what it does, right? It is closely related to product requirements. It is closely related, but is more specific because it's what emphasizes the features and operations that product will meet for the end user. So that is where it becomes a little bit different from your requirement. All right. So at some point I will still pause for questions, but I believe we've gotten that definition. So when we talk about product functionality for this, what we are working on now, the enclosure will have a dual use case. So it's something that we want to make it, it could be a standalone, it could just be on its own, or it could also be put into another device, right? So that's what we simply mean by dual use case. And the second one is the charge completion indicator. So on the electrical side of things, this will be explained to you, but on the aspects of maybe the mechanical aspects, the design of the enclosure and the rest of that, what you're basically more concerned with now is how to ensure that the indicator, which of course is, everything is happening down on your PCB, you are able to see. Remember, you are building an enclosure now to cover this thing. So how do you get to see what's happening inside, outside? Because you are viewing, you're interacting with it externally. You're not inside the enclosure, you're outside, right? So how do you get to interact with it? You're able to see, just like in your phones or maybe your chargers, you see a red light or maybe white or green telling you, oh, it's charged or it's charging, it's not charging, it's full, and all of that. So that's simply what we are looking at. So I would say the charge completion indicator. So we have that in mind, as at the end of the day, whatever we are building should be able to have this kind of thing to make it to make the user who is at the other end, to be able to interact effectively with the product. Now the last one we have there are many of them, but I just had to pick out the ones that kind of relates with what we are doing immediately. So we have a slotted vent for self-cooling. So if you remember during the requirement stage, we are talking about a way of achieving natural convection. You see how that term was? It's kind of vague. It's you could achieve that in many ways, right? But now we are being more detailed. That we are going to what is the product at the end of the day, we have some slots to allow for air to go in, and then you can achieve the natural cooling. So immediately, since we've seen this functionality, I'll now take us straight to how we now came up, or how we have been able to now come up with some design constraint. Because the first three things I've just mentioned, the requirements, the functionality, and the specifications, are all things that you have to now merge them and then extract very useful information to guide you as maybe the application engineer or the technical specialist or the design engineer, whatever term it is. But as long as like you're the one who is actually probably going to implement these things that you've heard, on the requirement stage, specification stage, and the rest of them. So you now use that, you gather that information and then formulate design constraint, because as you are working on the go, you will be saying some of those things that are like, oh, I can't do this because we are trying to achieve this. That's basically what we mean by this design constraint. So the first constraint, very, very important, is the availability of the PCBA. Now take note, not just the printed circuit board now, but the printed circuit board assembly, right? So the electrical designer has done his part. And for you to be able to really have that understanding of what is happening where, who goes where, that's what connections will happen where, and so on and so forth. You have to have that form of, kind of 3D aspect of the design you've probably seen on the 2D, the schematics, and all of that. So the PCBA that is available to you will directly influence some of the things that you will be able to do. That is why it's a constraint. For instance, you're trying to achieve a particular size that has been stipulated on your product specification, but the PCBA file is already higher than maybe the 500 by 500, for instance. Automatically, there's nothing you can do. So it means you have to probably interact. Of course, that's how it goes. It's a two-way thing. It's not just you're not just one man, like it's a kind of a one person trying to get this thing done. You also have inputs. The electrical designer has input, and every other stakeholder, that we ensure that design comes into a functional one, or should I say is a success. You understand? So this is the point where you will have to probably go back to the electrical design team and then say, oh, I can't get this size. There's no way I could get this specification, right? Because already I'm constrained by the size of your PCBA. So these things are very simple. If you see how I just put it, you understand how we mean, oh, being constrained. I can't do this because of this. As simple as I believe we've gotten that. So the next one is the selected manufacturing method. So in this case, you are looking at FDM, which is Fused Deposition Modeling. So it's basically just, if you're familiar with additive manufacturing, or even if you're not, you should just know that this FDM here, or FFF, is simply just one of those technologies that we have as additive manufacturing technology, or should I say one of those techniques rather that we have under additive manufacturing technology. I think that would be the right term. So if you are to use, for instance, FDM or maybe SLA or SLS and so on and so forth, there are so many of them. Now, they will directly impact or influence how you will go about your design. That is why they are design constraints. They have rules. So you have to go by their rules. If you're not going by their rules, you're simply just wasting your time, because when you are done designing, you will not be able to get it out. As simple as short. That is basically how it works. Even if you're even going out of maybe additive, you're going into other manufacturing technologies, maybe subtractive, or maybe even formative, like injection molding and the rest of them. They all have rules that guide how you are able to get something out. So if you're designing for SLA, and you're probably using SLS rules, of course, you're on your own. All right, so move ahead to the next one, which is the adopted IP rating. Like I said, we saw IP 30 because we are talking specification. So that was very specific, right? But now in terms of constraint, is a constraint because it means, oh, for instance, IP rating 30, that's 30, tells you that something that is higher than 2.5 millimeter cannot pass through that thing. So if it is smaller, it will go through, right? That's if there is a hole, for instance. So something that is higher than that 2.5 millimeter will not be able to go through the hole. So it means that even the hole you're using has to be probably smaller than 2.5, because that's like the range now. You understand? And then the 0 at the back, which is now talking about the access that a fluid can have into it. Of course, 0 stands for what? There is no protection. That's what it means. There's no protection against what? Fluid. So it means that what we are about to make, if you should maybe dip it inside maybe water or something, we are going to fry the entire board, and the system will get bad. So that is what a design constraint, because if I'm to achieve a particular maybe thing that has been mentioned on the requirement stage or on the specification stage, the rating that I am adopting, which would influence how I'm going about the design, you understand, will also have an effect. So lastly is the proposed use case, right? So we say it's going to have dual functionality. That also means that I have to also make some considerations during the design. So finally, what we have on our screen now is just a few quick renders of the final product, how it looks like. So at this point, I'm going to stop and allow for questions. Mr. Tolu can help me moderate that. Thank you.
All right, thank you very much, sir, for your presentation. I have already asked in the chat section someone who, if there's any question during the presentation, you should gather it and it will be taken. I don't know if Mr. Eduki has done that. Feedback, please. Is Mr. Eduki there? Okay.
Any questions? Does anyone have any questions? I think no, nobody has questions for now. Or whenever you have questions, you could send it across so that I will just be stuck on it. Connected just. Okay. So does anyone have questions?
Okay, if there are questions, why not let's pass them into Mr. Eduki so we can take all of them together.
Okay. Okay.
Anyone has questions, just pass the question down, then maybe when you don't in the next section we can ask.
So all this program and no question. Eh? No, so you're dividing. Your head is right. If we don't, your head doesn't. You guys choose engineering. Your father, you tell me anybody's father that was first.
There's no question now.
This question is very satisfying. So okay, that's fine. We have questions, put it down so that you can write it down and give it to you. We really want to know go and ask the question. But the question, you need to examine question you have. But at the end of the day, if you guys don't have questions, when they are true, I will be the one to ask them. And then it's sensitive. That's one thing you know, say whether you want to know. or there's something from the village. So, but that's fine. So, see, there's no place for everybody. And let's go to the project.
Okay,
Okay.
if there is no question, I think we'll be going on a break. That's right, Mr. Funny.
Before we go on a break, we could just start a little on the technical aspects, then probably pause. I don't know, we've spent up to 30 minutes already, have we?
Yes, we have about
Okay,
30 minutes.
Oh, yes, so we can go another 30 minutes before the break.
Okay, then.
All right. Okay, so thank you so much. I believe we all understood, the things I said. Probably even used a very common languages, so it doesn't have to get complex. We are all here to, get something, learn, and then, take something home. So that's fine. So the next thing we are going to be doing now, we are going to move to the technical aspects. So we are going to start working on, or should I say, see how we get some of these things done on Fusion 360. Just before I continue, I don't know, I would like to confirm, Mr. Felix, are they going to be, do they have their systems or do they just watch?
They have their systems, so but I think the first I think you guys should be able to go through it first before they start doing anything. But
Okay.
you need to
right.
understand. Yeah, so
All right, that's fine. Thank you. Okay, so I will just, pause my sharing and then reshare my Fusion
Thanks.
screen. You're saying something?
no, go ahead, go ahead.
Okay. So I'll just pause and reshare my Fusion 360 screen, and then, we'll see how far we can go for the next 30 minutes before, we get to go on a break. Right. So just a moment. I believe we could all see my screen. Just before I continue, please confirm if you could see the menu. I'm right clicking to see if you can all see. Are you seeing any options moving up?
I can see your screen, sir.
Now, I mean the options itself. That's a context menu now.
The marking menu is not showing.
The mark menu. Okay. Right. Comment, please.
You probably want to show your entire screen or something so that you capture that too.
Yes, that's true. That's true. It's visible now, right? The mark menu is visible.
Yes, please go ahead.
All right. So thank you, guys. So next we are going to look at how we can, get to use put Fusion 360 to work, to help us get our products out. Remember, it's a tool, a product design tool. It won't do the thinking for you. It's whatever you put in that is going to give you at the end of the day. All right. So we are all, familiar with this interface by now. I believe we did that yesterday. So I'll just quickly point out a few things for us. Because in my head, I want a situation where when you're also going about your own design, you're playing by the rules, you're going about it the right way. So along the line, at some point, I think I would still be, giving us some, tips during the, entire design session. So on the top left here, of course, we all know, we are showed that this is this is where we have our team. So I'm currently on the team called Introduction to CAD, for instance. And then on that team, we have a set of folders. You can see electronic PCB, generative design, and so on and so forth. So these are sets of folders. So I'll quickly just create a new folder for what we are about to do now. So I'll just call this, say, Futsal 2024, right? So I've created a folder on which I want to save my design into, which is still a subset, or is still under the project called Futsal Virtual Workshop. So this is a folder, this is a project, and this is a team. So that's basically what I just wanted us to know. So we don't mix it up, because sometimes it could really cause a lot of problems. The folder, the project, then the team you're on. All right, so I've created the Futsal 2024 as a folder. So the first thing you probably want to do is you also know that, because this was also shown to you yesterday, that you can use this to come up with a new design page. You click here, you have your new design, or you can also go to your file menu and then you pick some of the stuff there, or you do Control-N, just as you can see here. All right, so now I already have my interface open. So I would close my data panel for now, so that we could probably have a better view of my interface. So hide my data panel, and then go ahead to do a save, a control save. So you can do Control-S, or you just click on save. So it's a good practice for you to, just before you go into designing, you save the design file itself. If you've used other CAD tools, it probably be called projects, different names for them. You understand? So you have to save. It's good practice for you to save that what you're about to work on, even before you even have any content inside, that's any data inside, right? So that Fusion kind of registers this into probably the location where you want to. In this case, you can see location here. It reads workshop training, now reads the project, which is this other one you're seeing here, right? So I'll just still call this our product enclosure. If that's visible, I click on save. So you notice this V not here, which is like saying the initial version of your design. There is no content in it. If I go back to my data panel, right? Okay, sorry, I think we made a mistake there. This should have been saved into this, right? So we can see, let's just correct that immediately. A minute. So we say save. So I'll say products. No. Sure. And I'll come over to here to be very specific. That's why we had it out. So I have to now narrow it down to the folder, right? That's the step we missed. So click on this photo. So you can see the directory now, and then you click on save. So I will just close this other one. Probably delete it out. So when you go into your photo, you now see the design file, right? Now this currently does not have any content, doesn't have any data inside, but it has been saved into Fusion. So that's is a very important step. Do not forget, we said cloud-based. So a lot of things can go wrong when you don't, get some of these things done and on time. All right. So the next thing I will do, which is like a rule of thumb, or like a number one rule, is to create a component. So I will call this enclosure. This enclosure design. So you could notice, or you might be wondering, why do we have standard, external, and all of this? So I wouldn't want to go to go too deep on it, but you just have to know that it could either be a standard file, so more like maybe a file containing your design, which is probably just something you probably modeled as maybe a B-rep. That's what I mean by that is a solid, maybe a solid model or a surface model and all of that. Those are classified, or those will be stored as what standard components. But if maybe it has to do with like maybe a sheet metal, probably have to come over to here and then select that you want this to be a sheet metal, and then a lot of things will, change in your interface just to allow you, carry out your sheet metal with design, maybe activities and the rest of that. So this other one you have here, external. Let me open back my data panel. Right. So if I should click on external, what you will notice, aside the name, is also asking for what? A location. So basically, this allows you to save a component. Yes, you're working on that component here, like on this page, this design page called product enclosure. But when you are saving it, it's saved outside. So it's going to be saved as an external file where you will probably access on this part where you have your words, where I showed us our file design files with the one we created Photo 2024, right? But if I should say internal, which is the route we are going to use now, it means that these components will be saved inside this product enclosure design file, a design space, and everything that has to do with it will also be recorded and saved. As its entire history will what? Be tied to whatever is happening within this space as the product enclosure design space, the one we created. All right, so we'll just click on this. And then you could notice that the radio button here is already on active or activate. So it means that if once you click on this OK, it will automatically take you to that file as the active file. And as we keep on designing, we are going to see exactly how that works. So I wouldn't want to dwell on that. Once we start designing, you see exactly why we need to activate something or turn off something and all of that. Okay, so we just call this, like I said, let's say enclosure. Right, so I click on OK. So you will now notice that the first file we had, which was product enclosure, which was just one component, now has this little brick here telling you that there is a component under a component, right? That's how Fusion works. So this automatically becomes our our assembly file. The highest of the highest when it has to do with hierarchy of file will be this very first one you're seeing here. That can make a lot of things work for you. That can also make a lot of things not work for you, depending on what you're trying to achieve during your design process. So if you notice, there is a dot on this other one, the enclosure design. You could see this little dot here. This is because this component is now the active component. So whatever I am doing will be recorded under this component. Are we together? So we'll just quickly move. Close my data panel for now. So we have our enclosure design. We've created a component called enclosure design. We've also saved this file to Fusion 360. So another thing that we want to take us through, definitely we are going to see how we go about sketching and then translating your sketch, which is like a cell now, to maybe a higher rank of, in terms of when you're looking at geometries. Because a geometry can actually be a sketch, it can also be a body, it can also be a surface. Those are all classified as geometries. So the basic, in that category will be your sketches, which is more like if you're thinking about it on the, maybe should I say biological setting, more like, okay, cell, your basic unit of life, and then maybe it grows into maybe your muscles, tissues, and the rest of that. I believe that is very clear. So the next thing we are going to do is there's something called parameters. And I believe my colleague mentioned this yesterday, where, if you could recall, he said parametric modeling and direct modeling mode, right? So he explained that, but now I'm going to show you what that actually means. That is the implication of you using any one of these modes. So for instance, if you come over to your Fusion, and then maybe you say you want to create a design, and then you start with this. It's called create base feature. So the moment I click on this, what you will notice is that there are some changes on my, my tabs, right? There are some things we saw which are no longer what here. So all the tools here are just what strictly specific to allowing you to make what direct edit. And that what that simply means is that Fusion would not record, would not capture the things you're doing. So this is our timeline, which of course he also introduced us to yesterday. Fusion will not capture those things for you. It gives you the freedom of changing anything anyhow, and it's more like saying there is no consequences, right? You can think about it that way. You just change anything, you pull out anything, and it works. You just do. It's more like a mode where you are allowed to remember. Think of it this way: you're just having a thought of maybe it should be this way, or maybe it should be that way, or maybe you should have this leg, or maybe you should have that hand. So it's not really formed on your head, but you're trying to get it done. So you could just use this mode to play around with the thing you're trying to get at. Then once you're probably say, okay, you now achieve how you want your maybe the design or geometry, or whatever it is you were building to look like, you probably have to switch back to what the parametric mode, so that you can now make you can now have relationships between every feature you're using, and you can have not just having relationship. The takeaway there is that you can have full control over what you want to have a relationship, or the things you want to have a relationship, and the ones you don't want to have relationship. You can have that control to separate between all of them. So I will just quickly remove this. I just had to do this just to explain to us something. So I'll just quickly undo, right? So move straight ahead to I'm making a sketch. For instance, if you should come to Fusion and then you want to let's say draw a circle, right? You want to draw a circle. Now you think of it this way: you have a pen, you also need a book, or like a place where you can use that pen on. So that place where you could use the pen on is what we refer to as plane. So you come over to this point, you will see something called on our browser called Origin. So if you turn it on, of course, the active component is enclosure. So I won't use this one up here because this one is what tied to the full, the highest assembly. So we probably open up this and then look for that same thing here, because each one will have. So you could notice that I'm doing this intentionally just to show you how most of these things would work. So you could see these planes. These are what you're going to be using to make your sketches, right? Where you could sketch on, whether it is inclined or whatever way it's going to be. These are the basic forms. So just like your graph, X, Y, and Z, as is, right? So now I want to show us how parameters work. So we could move ahead to creating parameters immediately. So think of it this way. Let's say I want to draw something on this plane. So I just click on this plane and say, maybe right click and say I want to create a sketch. So I click, right? So of course, now I am on the sketch mode. If you have to pay attention to how Fusion works, because it could only it could cause a lot of problems. I was on the solid editing tab. This is where I was. Now once I did that create sketch, Fusion presented me with a sketch environment, which if you should look at this other part, you could just find it there, right? So on the sketch environment, of course, if we use AutoCAD and some other design, you all know how most of these things work: lines, modification tools, constraint, and the rest of that. So I'll just move ahead to I'll pick up my circle. I just want to show us how parameters work so that we can go ahead to start creating one. All right, so I'll just select any place and then pull out and then keep my circle. Now I'll go to my f of x, which is where everything that has to do with parameters are recorded. If you notice, all you could see here is called model parameters, user parameters, but there is nothing under. It's just a blank page, right? So how about I do this? I come over and then I pick on dimension tool and then select this circle. And now I want to be specific that I want it to be 50, enter, right? I've clicked on enter. Now you can see that the circle is 50, right? So go back to that place. Now there's still nothing on my user parameter, but there is something under the model parameter now, under the sketch, because if you take note, if you just take, paid attention, you see that we just created a sketch. So under that sketch, you could now start seeing something called D1. It has a unit, it has an expression, which is the 50 mm I used. So this is basically so that you could know that every single thing that we're on the parametric design mode now, Every single thing you are adding, maybe, oh, it should be this high, it should be that small, and so it's all recorded. As long as it's what is contributing to making that design what's a success, that's is contributing to the shape or size of that design, you're going to have them what's captured here under variables. You this as we keep on designing, start seeing this what's increasing D1, maybe D25, and so on and so forth. But how about the user parameters? How about the user parameters? Now, this is what I'm going to do. If I want to create a parameter that I want to use over and over and over, probably for different purposes, right? What I need to do is not to rely on the model parameters, but rather I create my own parameter. That's why it's called the user. So you go over to your f of s, and then now you click on this positive sign here. There you can now say, okay, I could call it, that's the name of the parameter. I could say circle diameter. We use DIA for short, right? DIA. So units, of course, what units you select? It's not just techno, it's not just length. It could be in angles, currency, and so on and so forth. Mass, you could see all of them. Power, there are so many. So I just have to point out, because a lot of persons also think that it's just, oh, maybe mm and cm. There are so many things that you could do with, this interface. You could see even up to inductance, magnetic field, viscosity, flow rates, and so on and so forth, right? So whatever it is you picked. So no, we are in the length aspect now. So we're dealing with cm and so on. So you just say, okay, let's say 45. So I put the expression. That's more like the magnitude now. And then maybe I wanted to do some computation, maybe some calculation. I could say maybe, for instance, times 2. So this is the difference between expression and value. I had to do that, so you just see expression, I've done what I want to do, but now this one reading value is now, okay, summation. After everything, what is the answer? Are we together? And now I can now use the comment section to explain, because in reality, most times we work with different persons, and you want a situation where your second or your first or whoever it is that comes into or has access to that design is able to see, like, just mere looking at your workflows, the processes, everything you're doing. He's having an understanding of what you're doing and probably why you did it. So I can come and say circle outer diameter. So automatically the person sees this is more like a comment. This one now you can do anything. It allows you the freedom of typing a lot of things. But for the name now, you probably want to do something like adding a 1 here. You see an error, it won't allow that. So I just had to also point that out, because these things also cause a lot of problems. So click on OK. So now you will see that there's something called user parameter by this name, by this expression, and by this value. So instead of using this other one, which was 50 model parameter, I come in here. It's asking me for a value. So I can just type, and then because this is the only value that we have so far in our database, so that's the only one coming out. So I'll just select let me do that again, sorry. And then click on OK, right? Why is it this way? Because I did an expression. I said circle diameter is 45 times 2. You get I don't know if you're getting what I'm trying to communicate. And so that's why it has just affected the total size. So one might ask the question, why didn't we use just the model parameter? Why are we creating user parameter and then we are still using it to probably try to achieve one? Now the truth is this. You see these two, the one up here user and the one up here model. Only thing you are going to find in model parameter are the things that constitute the design itself. So it means that in user parameters, you could have lots of parameters that you created and you are not using them. They are just there. So that whenever you want to call on it, probably you want to multiply it with something else, or use it to do summation, or use it to do some expressions. You understand? Even like if, then, and all of that. You understand? You could call them in and they will give you exactly what you're looking for. But the only ones that will be recorded here are the ones that have been used to make up the design itself. So I believe that is clear. So I'll just, move on from this. As we proceed, we keep on seeing how the whole parameters work. So one more thing I would like us to know is when you're working on Fusion, for instance, you could see that I could drag this circle all around. And the reason is because this circle is not constrained. It is a bit constrained because it has true size. That's the diameter now. But it's not totally constrained, right? That's what I'm trying to. So for instance, if I come here and say, okay, what's the distance between, as I pick up a dimension 2 and say, distance between this center and the center of my circle, and then I pull this out and probably put a value, let's say maybe 9. Can you see it's also constrained, but it's not still totally constrained because this circle can move in this direction. Now it can't go this other way, left to right, but it can go up and down, right? So I still need to probably use this and say, okay, what's now the dimension between, sorry, take that again. What's now the dimension between this circle, this center, and this other center in this other direction? So immediately, even if I didn't put maybe my value is whatever I want to put, maybe 5 or 9, you will just notice this black black coloration on the sketch. If I try to move, it won't move any longer. So I'm showing you this because by all means necessary, sometimes I know sometimes they could be broken, but you should always try to allow your sketch to be constrained fully, so that it will make your design stable. Because this is what will happen if this was not this way. Let me delete this first one, for instance, and then let me add a form that's a body now to the sketch. So I'll just say, for instance, extrude, and then just pick this up and then click on OK. So once I've done this, yeah, it looks fine as everything is okay. But imagine someone came into your design and then by mistake he had access, or he has seen this sketch. Are we together? And then he does this. Just watch. Now I'm pulling the circle from its midpoint. You've done a very perfect design. You've even done up to the paperwork. That's the manufacturing drawing, for instance. And then someone just comes and does this and pulls this sketch a little away. This is what happens. The model, everything now readjusts to suit the new position of the circle. It might look funny now, it's because it's just a circle. But imagine that you have done a lot of work to tie this to maybe another body that is having maybe some curvatures. And someone comes and after you've done that perfect work, just by pulling one sketch, right? Just by pulling a sketch, you have that happening. So it's going to mess up everything. And Fusion is a just the way you were showed yesterday. You have design generative. So it's going to update that same way, downstream. So maybe you've done your design and you are now here on drawing. You are creating a drawing file. That updates we have done by moving this will also update down to the drawing file, mess up your animation, because even the animation you are trying to create will also have everything has shifted. You're doing something on the manufacturing simulation, whatever it is, that as long as it's tied to this file called enclosure design and you have moved the sketch and the geometry has readjusted, everything changes. So it is both beautiful and could be heartbreaking. I just had to point that out. So having said that, I will delete all of this and then we'll commence our design proper. All right, I think, is there any question before I move on, please? Atolu?
Yeah, there should be questions. No question.
Mr. Edoki, please hand over the questions now.
I know what you guys think. The approach is just the same sometimes could be the question of, why we and most of you guys who probably have played with some other software, we got vector or things like that, like you see a different approach. I remember what I said in front of you. What you're supposed to learn to be you're not supposed to watch it, you're not supposed to do it. It's not supposed to be both minutes or 5 minutes. When you should be at the office. So what we're trying to do is trying to drive every single thing to plan. Go ahead and think about this one and just moderate the way you're talking about. But when your design start getting bigger and bigger, it is more design.
Can check the income message.
Anybody that wants to ask questions, we use this.
I already posted some message.
Okay, so the mic is on, so we're already hearing me. So one comment out, it's about how to do that. So it's important that guys you understand that. If parameter things that actually, what people say divide device. People think that you hold formulas and write your like formulas like calculations right into the parameter. Like every single thing, not with relationship. Say, oh, one thought of this is what to this. At every point in time, that relationship and then as far as you change it for no one on the maximum change. So any design errors go to the crash almost to zero. So you are in charge of what you're doing. You're not seeing surprises. And then when we go into the point of construct, you also want to see that. So it's important for you to really check out on this. Before most times, if you basic class, you just maybe basic class, you don't take this approach. But why am I taking this approach for you? Is for you to really understand that starting with the hard tools and the beneficial for you. Because in 6 months time down the line, you could actually be performing more than somebody who is 1 day down the line. Right? I have seen projects that people take 2 weeks to come up with. And then one mistake they have to do it. And then the project crashes, they have to start afresh just because you follow the right way. So it's important. So now I respond to your questions, and then I think everybody else been able to answer. So guys, go ahead. Thank you.
All right,
Alright,
so
so look,
we about
okay, go
we
ahead.
about few questions, 3 questions, 2 rather, I have for now. The first question is, from the pictures shown, is additive manufacturing limited to plastics only? That's question 1. Question 2, under material types, are these the only materials used in 3D printing, or are there more? Question 3,
Alright, okay.
focus more on IP rating. So these are the 3 questions we have for now.
Alright, so thank you so much. That's a wonderful question. I love the question. Okay, so question 1 was he asked about if it's just for plastic. No, it's not. Actually, there are so many of them. We can also do 3D printing of metals, right? All those ones also have their how they will go about it. For instance, for plastics, they could come in form the materials, the raw material now come in form of what we call filament. Like, but in terms of metals, you're probably looking at what's metal powders, right? You understand? So definitely, there are about I think 7 and counting of the technology we are looking at. For materials, we have the ones for plastic, we have technology for metal. We even have currently the one for composites. I believe you're familiar with what we mean by composite materials. You have multiple forms of materials probably meshed together, and so on and so forth. So that's for the first one. The second one you asked was if that's the only 2 kinds of material. No, there are so many. In fact, there are so many of them that we have to even classify them based on use cases. Okay, if you're looking at something for mechanical application, probably we try this. For instance, we have the PLA, and the PLA you saw there already has a lot of variation. There's PLA plus, there's PLA tough, there's PLA normally. You understand? The PETG you saw there, there's also PET like PET. The G there is even like an upgraded form of the PET plastic. We have other ones like ABS. We have other ones like nylon, not normal waterproof, right? We have CPE, the ones that we use for that one. Now we are looking at use case like buildings, you understand, for some form of structural stuff. And there are so many of them, right? So I will even leave that to you to go and do your own homework. So you could just use that to also learn and get acquainted with most of these materials. What you basically do is you could just say, 3D printing materials, you look at them, you look at use cases, you look at the unique qualities, because each of them you will hear something like, oh, this one has better resistance to heat. The other one, better finishing. You understand? The other one could be, the heating temperature that is okay, maybe not so high. Therefore, it is not very, it's not common for it to have defects like warping. You understand? So there are so many things that come around. Just think about it like every single material that you're talking about has, properties embedded in them. So you're going for it. That's why we even mentioned that you're going for it because probably what you're trying to achieve in the design, that material has that uniqueness, is one of the best in that area. Or want something that has structural integrity, strength, durable. You understand? Let me give you an instance. PLA is very common material, but it has a bit of a brittle, effect on it, especially when it stays over a long period of time. So now we are considering it. Let's just say maybe the same material, the same thickness. You understand? Not like maybe comparing a 4 mm PLA with maybe a 2 mm PETG. That will not be a fair comparison. You understand? So let's say same material, same dimension and everything. You understand? So when you look at both of them, you find out that PETG on the other end is more durable, has some flexibility. So it means it has the ability to probably maybe readjust itself, probably if it's a little bit deformed. But on the other hand, your PLA plastic would, after maybe exceeding its yield point, would do what? Just break. You understand? So these are things that I'm very sure we are familiar with. Just your material science and what's it called, strength of material and things like that. You will get to see. So once you're reading the material, you're reading the function and the use case, you get to know them. So I believe I've answered the question. There are many of them, like I said. It's not just PLA. And the third question was, can you remind me, Tolu? Can you remind me, Tolu, the third question?
Let me go back to the question, the chat box. Okay, the last question is about IP rating. There's one more question anyway, if we have time to.
You can add as well, it's fine. It's fine.
It says the third question is discuss more on IP ratings. And the fourth one is in product functionality, you mentioned dual use case and gave an example of standalone products. In instances where a product is not standalone, that is, it's dependent on an existing product. What happens when the device follows all rules but has an issue working with the already existing device? Do you need to keep the existing device handy while checking it with the product you are designing for overall functionality? I just hope you can understand this question.
It's quite long, but let me do this. He probably has to clarify a little some things, because from what he said, we mixed up two things. If you're coming from the technical side of things, that's having design that is probably a standalone and a design that is linked with something else, that's a different case. But the one on the slide which you saw was not about this technical aspect now. Rather, it was even more on the use case. For instance, is it something that is a finished product on its own? You just get it out from the market and you use it for what you want to do. Like you could probably place it on the table, do whatever it is you want to do with it, and it doesn't have an issue. Or it will be something that you can also maybe have to plug to another thing, probably put it inside another, you know how these things work with maybe modules and the rest of them. So you're probably getting this, yes, it's a product on its own, but it can be housed by another enclosure. That's what I meant by the one you saw in the design. So you have to clarify which one of them you're asking. That's for that. And then the other question you asked, let me quickly answer why he's trying to clarify. The other question you asked was about the IP rating. So like I said, I don't like to allow most of these names to, when you hear terms like this, it's as if it's one very big thing, but in reality, it's actually just something you could understand. Right? In reality, it's something you could understand. IP rating. Ingress protection. What do we mean by ingress? You're trying to protect something from penetrating. So like I mentioned, two things are very important. The first one is physical objects, pin, human hand. For instance, you know how, although I wouldn't want to use a transformer because that is even a very, it's a tricky one. So let me just use maybe your TV, right? There are the delicate parts of it that during the design, or when you have it as a full product, you find out that you are being there's in the design is incorporated such that you cannot have access to certain things, probably except you open up the device. Do you understand? Another reason will also be probably to protect you from physical shock. You don't want something that somebody just turned his hand or leg by mistake, and then as he just drops on your products and he's gone, electrocuted. No, right? And now I'm not talking about where we have defects. There are cases where you could have issues, maybe you're grounding, those are electrical stuffs. I'm talking about something that is actually working very well, but just a mistake on you as the designer, incorporating something that should ensure that somebody does not maybe just put his hand. For instance, remember I always like to say when you're design as if you're designing for mad people. It's funny, but someone might just want to put his hand somewhere. Why do you think most of your electric fans, like the ones you use, have protection against the blades? If it's not there, you could just be maybe talking and you're playing and you just put your head straight on it and you get wounded. So just be by that ribs around it is already protecting you from having that physical contact with the main, especially the part that is delicate. Either maybe the part will get damaged or you will get damaged because there's going to be a damage. Either you understand. So that's simply how you look at it. Ingress protection against penetration. Now, what are these things that you are more concerned with? I said there were two. For IPO, we also have other ones used by, how these things work. Just like you have ASME, you have other, like maybe, the one for, what's it called, ANSI, you understand? And all those, different forms of specification and all of these that are tied to maybe particular countries or like maybe in Europe, they use this standard for social design, you understand? So all those things also play a part. Like this IP rating is not the only one. We also have the ones that are used in US, you understand? Which is similar to IP rating, but it also comes with its own packages. So it's just like a code. You have to interpret the code. You understand? For the IP, so that we don't digress too much. For the IP rating, I said two things. You protect against physical contacts, that's obstacles, objects, right? And then the second one, you protect against what? Fluid, right? So when I say fluid, so you now know that it's more like all encompassing. So even as basic something, even coming from like dust, you hear something like terms like things that we are familiar with now. You say it's dust tight. What does that mean? You understand? Those are the things. So maybe something you're going to use outdoor, and you don't want a situation where that you have maybe dust getting into the whole thing and damaging the entire component. So an IP rating of something for a product that we have, that will prevent even dust from getting in, that's very high. So you're probably looking at maybe IP 6 something. I don't know if you're getting me. So you could just do your homework, like I said. You check on them, you see the different numbers and what they mean. Then you adopt it for what you're designing. You understand? So I said fluid are the major concerns. Fluids, that's water, dust, air, and so on and so forth. And what? Object, pin, human hand, whatever it is, all classified under that aspect. So I believe I've spoken about the IP rating, and I don't know if he has clarified the question, then we can move on. Thank you.
Yeah, thank you, Ofonime. Just to add a little few things is, so that you don't get to see it as too much technicalities, right? When you hear IP rating, with some phones you will see, or some AirPods you hear, you see water resistance, right? Some will see fully water resistance. Some will see partial. Some will see splash water resistance, right? A splash, not submerged. These are the things you see when you are buying products. Now, all these things are all about the IP rating. But IP rating is not for technical like you. But for the user, it doesn't know what the IP rating is. So we're not going to be communicating to you as a basic user because you're the one bringing, because each of the numbers means something. But when you hear dust resistance, it means that it doesn't allow dust to get into it, right? These are all part of the things when you talk about the IP ratings and all that. So when you are designing something, you're asking yourself, what is this thing going to be maybe used inside? Because you know that electronics that are inside water. The kind of IP rating to have, be the one that is just say, oh, take it away from fluid or this. There are some products you refer, say, please remove it from damp area, right? So those damp areas are like there's higher possibilities of having moisture, and those moisture can enter into those products, right? Just change, there's no issue. So those things can enter into those things. So these are things you have been told, oh, stay away from this. But each of them, why it will tell you to stay away, or oh, it can be within this environment, there's no problem. It's dependent on the IP rating. So it's a topic on its own that if it's a course, it could be a course for 2 semesters, right? So it's great, but it's very critical, for what you guys do. It's very critical for whatever you are designing, because you can't just design something mistake or don't even know that whether it's what flash on it, whether it's going to get into the computation back. And that will also determine the kind of design. Because if you say IP rating of a particular level, right? If you want to achieve an IP rating of a particular level, that can also affect the internal component. If the heating is high and you want to have everything ramped up, that will also, make you to know, oh no, I'm not going to use transformer, is relative. I'm not going to, because you need something that will have maybe a surface, maybe just let me say, heat sink and just a surface cooling without any vent coming out. Right? So these are the things that we talk about constraints. Some of them, and you tell me what you are doing, just go to CAD and just sit down and drawing something that you got quickly. Oh, I have drawn a CAD. I have drawn this thing. These things are just cards. They're just basic things, just for free, just like a graphic design. That's nothing bad. So when you're saying go to the product or new product design, all these considerations must come in, because that is where you say you have innovation that can get into the market, or somebody can just buy. So these are all three things that you need to know, the rules and basic things and all this. And when you're going to question, now, okay, this is consideration I need to make. Because question, like they say, is that big and bigger. Now what you put, you get. If you put backward, you get something. It's just like a tool that enables you to make you work smarter. But if you're not smart, you still will be stupid. Thank you. All right, so I don't know if there's no further questions. Go ahead and or we can go on break. I don't know.
All right, thank you so much, Mr. Solo.
There's one more question here we have. That's the fourth question. I believe he has modified it. Let me just read it out. It says, from what I understood, product specifications are specific design aids that achieve the requirements, and product functionalities are features that enable the users to interact with the products. The question is, how do we fix compatibility issues when we are developing a product that is dependent on another?
All right, so by compatibility, I don't know if that term is clear enough, but are we together?
Let me read it again. The main question is this: how do we fix compatibility issues when we are developing a product that is dependent on another?
Again, this is also quite still vague, because if you're talking about from the product level now, not on the technical side of things, I believe there are a whole lots of stakeholders.
All these excuses are not out of. You cannot, anybody that is paying attention in this class, we even get these things out of this stuff. We're not even started doing anything, and you guys are running around. What if you want to start doing something? Disconnect around.
Maybe we can all see my screen.
Yes, we can see your screen, sir.
All right, so we've spent quite a lot of time. So I'll be a little bit snappy. Probably I might not be too detailed on the explanation. I will try my best, just to ensure that we get something done. So we are still on the, parts of the parameters, and what I will simply do now is to just go ahead, create it. We can all see how I'm creating them, and then I will proceed to, other, things. I don't know. Someone saying something?
No, you can continue, sir.
All right. So we've all seen how I did work on the explanation of the parameters, the user, and co. So I'll simply just start creating one. You just go to your Fusion. I will remove this other one. We use this for description. So start, then we'll just create all of them that we'll be using for the design, and then we'll see how we'll call them in. So the first parameter I want to create is going to be a parameter that will help us tell the size of the enclosure first of all. Yeah, we are not adding all the features yet. We just want to even have that glimpse of how big, how small, and all of that. So in order for us to get that done, I'll do this. Remember, we said one of our constraints is the PCBA as the assembly, the PCB with the the components on it, the 3D. So that means first of all, we'll have to get that file, and that's the beauty of Fusion. Everything is integrated. So I don't need to ask anyone to send me a file, as long as we are both working on the same project and I have the assets,
Sorry.
Right?
Sorry, sir. We lost you 3 minutes ago, sir.
Where did you stop?
When you were doing the dimensioning.
All right. So I have not done anything yet. I'm basically saying that one of the constraints we pointed out earlier on was that the PCBA file, right, is very critical in order for us to be able to even come up with a true size of what our enclosure should look like. So it means first of all we have to get that done. We have to get the file in, and then we'll go ahead to create parameters that can help us tell the true size of the enclosure we are building for the PCBA. All right. So like I said, I was trying to point out that Fusion, one of the beauty of Fusion is that having all the files integrated. You understand? So you don't need to go to get maybe being sent the file separately or anything for you to be able to work. You can work directly on the file that maybe the electrical design engineer is using for his own design. You can leverage on that file directly where you are and get to work. So whatever he does on his own end, that maybe a change on his own design will also reflect on your own design, as long as there is a link between both of them, right? So I'll quickly go over to get the PCB file. So I'll click on my data panel. Sorry about that. For some reason it's not opening. I think I probably have to reshare my screen, please. Sorry about that. I think there was a little glitch there, maybe a network issues or so. So we just click on your data panel. It pops up just as it has done. And so I have to now, of course, we created this Futo 2024. I've created this design file, a standard design file now. So we just navigate. Okay, this is the PCB file under this folder, electronics PCB or design. So this is the file, right? So one beautiful thing is, if you notice, I'm still on product enclosure, which is coming from this other folder. You need to understand how these things work, because they could really mess up a lot of things for you by design. It's quite easy, but just that understanding will also guide you on how to go about generating workflows for your design. So this is where the one we are designing is. Why this is where the PCB is. So they are on separate folders, but on the same project, right? The same project, right? So while I have assessed this other design from a separate folder, and this is currently what is displaying on my screen. Remember, there's nothing inside. We haven't designed anything yet. I can move over to any other file within this project, right? So in this case now, we still come over here. This is the PCB, right? So I want to make use of this. So the very simple way to go about it is just simply drag this file. Are we together? Just drag this file from your data panel straight to your GUI. You understand? And then you wait for that to just update. So what you will notice is that I now have a PCB from the PCB design folder currently in my own probably let's say now let's look at it from let's say maybe the mechanical design folder, for instance, right? So I will just click to accept this. I click on OK. I'm not changing anything. I just click on OK. And maybe just to avoid the confusion, I can just head back to my own folder, just keep it there. I'm not opening this, I just went back, right? I can close this now. What you need to take note is this link that looks like a chain on your browser. You see a little chain icon. So it's telling you that this file you're working on is linked to something else. That is linked to another design. Like, so you're leveraging.
Sorry. The light went off. Let's just reconnect the light.
Oh, you head up to this point, right?
Yeah, but we had a constraint at this PCB. This PCB you opened just now.
Did you say how I got it in?
Yes, how did you get the PCB?
Okay, so are you good to go now?
No problem, sir.
All right. So I will just undo this. I was trying to say that you have, we all know that we are working on this folder called Photo 2024. And this is where we have our own design file as probably maybe a department now, right? And you want to leverage a file because this is more like when we talk about, the files being integrated, collaboration, this is all we are saying in a very basic language. Now you want to work with someone's file, probably done by electrical design team, which is under this other folder. So I said one of the ways you can do that is while you're on the current workspace, which you want to have your design done, you can just drag from your data panel straight to your GUI. And that is all. You have that file in your workspace and it is linked. You click on OK to accept that. It is linked. You can see this chain icon by the browser, right? So this is telling you that this file you're working on is linked. So if the electrical design personnel changes something on his own design, it's going to also reflect on this part. You will see an icon on the top left here telling you that this file you used before is outdated, that there is a new version. So all you need to do is accept that and you continue working depending on the kind of changes. Some changes can be catastrophic, some can also be mild changes, right? Okay, so I will just close the data panel for now. Now, what I've just done can be done in many ways, right? Another way, but I won't want to go too deep into that, is for you to go over to your insert and use what is called insert derive. But this is also a different workflow. So one thing you will want to do is to understand how they work before using them so that they don't mess up your design at the end of the day. I'm getting some noise. I don't know. Is someone speaking?
No, I'll just mute myself right now.
Yes, but please stay close to it so that in case anything goes wrong. All right, so now we have the design in our workspace, right? And like I said, it's linked. The next thing we want to do, remember we created a component called enclosure design. So if you're very observant, you will notice that enclosure design has just had the photo, that's the PCB design brought under its big, and this is as a result of it being active when I did that activity. You understand? So it has now become a sub file or a sub component under enclosure design, but this is not desirable. This is not what we want to do. You understand? So just did that on purpose. So all I need to do is to go back to the overall assembly. I've did an undo on what we just did. Go back to the overall assembly, which is product enclosure. Activate it. It's very easy. Just click on the button you see by the the radio button. You go back to your data panel, perform the same action. Please notice, or you can just spot the difference when you look at the what's it called, the browser. So I'll close this, I'll accept this and close this again. If you notice now, you can see that this is what on its own as a component, and this is also what a component. All of them are now what children under what the parent what folder. I believe that is understood, because that can really what mess up a lot of what things for you. Now, why is this other one reading as a although it's under the parent, which is product enclosure, it is also having subcomponents. Is of
Sir,
course
we didn't get how this component was added again. You dragged and dropped it. Or
yes, exactly.
file. Do we have to have access to the file, or we can we have
Definitely,
access to
you need to. You mean for your own work, for you to work with it?
yes, like a
We
sample for
will send you the file. We can't do that. I don't think we'll be able to do that now, looking at the time and everything. We will send you the file to practice on your own, right?
Okay, sir. Yes, sir.
Yes, you can even add you up on the team. It's something that we'll take care of later. But I think for now, we just have to just maybe probably listen, ask questions, listen, and that's how we just get it done, right? Hope that's good.
This
That's
question
fine.
should
Thank
come
you.
up.
All right.
Presentation.
Thank you. All right. So like I said, we now have the PCB file. It also has its own subcomponent, and that's not really our concern now because we are not the ones that designed it. So whatever is a subcomponent here it was done like the file came that way. I don't know if you're getting it. So you don't have to also you brought in the components separately, but it's looking as if there are other components under, right? So these are all what children under what the parent what folder. That's how the files in terms of hierarchy works. So now we have this. We simply have to do something. Now, we want to read, remember we are building like a house for this, right? So probably want to know how high the entire, what's it called now? The entire component is, right? The entire, like the file, what's the highest point, what's the shortest point, are there holes on it and stuff like that. That's what I'm referring to. So you could also see these different things here, transformer, heatsink. I'm mentioning these ones because these ones will concern us, right? Not these other ones are not really for that. That would be when the electrical person is taking it. But for the heatsink, you need to take notes of that, the transformer, because they heat up while they are, in operation. You take note of the hole, because the file, the PCB will be gripped to your enclosure. And how that's going to be done is not going to be electrically. You are the one that's going to handle that. So that means this hole is very, very also important to us, right? So the first thing we'll do is to just take some measurements, right? So we could just go over to this point. You click on inspect, you click on measure, or you use a shortcut, which I like doing. So you just click on I on your keyboard, and it will also pop up this what's it called, dialog box, right? So you could just do a quick measurement. I'll tilt this a little bit. So you could say, okay, from the surface, the top surface of the PCB, right? The board now, that's what I'm referring to. So the bottom surface. That will tell me what? The thickness of this PCB board, right? So if we see a distance here, reading what? 1.605 mm. So you think that one now concerns you, right? The next thing we are going to also measure will be the height. So let's say from this board now, right? From this board to the highest component we have here, of course, it's very obvious the transformer now is the highest component. So I'll just do the same thing we have done. I click on this surface. I click on this surface as well, right? It also has a reading. We could see 34.65 millimeters, right? I take note of that too. Take note on how I'm taking the reading. So I have done the board. Now I've done from the board upwards. So I have covered that measurement from this top till this point, if you were following. So that means the only thing remaining for me to take is from the PCB now, because there are cases where you could also have things, on this design, of course, it's made such that we could use it for learning. So it wouldn't be a very complex design. But there are ones where you also have things running under the PCB. And you can't during your design ignore them. You can't even afford to ignore them. You understand? So in this case, we'll just take a measurement from, okay, since we have some metals protruding from probably the components upwards, right? So we just do a measurement, okay, from the PCBs, from the board, right? That's under the board now. Then I will just zoom in, right? To locate maybe the peak point. So we can, let me keep on the side view and turn this back in. We could see the highest components on the, that is binet, or on the lower section. That would be this one, right? So all I simply do, if I don't even want to go that way, I can just activate my show snap point so that I can be specific to just pick here, right? Turn on that, just pick any place here. Now this will pop up the dimension, but it's going to be what? Slanted. So what I will probably do is also to look for, okay, let me do that again. Just 1 minute, please. So I'll click on this point and probably click on this point as well. So you could notice that there is kind of a highlight at the middle here once I move my hand to this circle, right? So I will hold Control on my keyboard so that I can snap that point. Are we together? I'm holding down Control, so it allows me, when I move away from the circle, I still see the point. That's what I just did. So I can now what? Click. Are we good? So this is what I wanted to show us. That's why I had to redo that. So even if it is slanted, let me zoom in again. Even if it's slanted the way you're looking at it, there's this thing called what? XYZ delta. So I can just what? Activate maybe the global what? Coordinate system. And then that will what? Give me all that measurement, both in the slanted form, the one that is directly straight, and what? Everything that has to do more like your 3D what? Measurement now. So we'll just zoom out a little and zoom into that point so you can see what I'm talking about. Right? See how the measurement is done. I'll tilt it a little bit. Okay. Tilt this a little bit. So we have one going slanted, we have one going directly up, and then we have another one going from this point that is slanted to this what other point that was up. So that's why you're having what 3 dimensions on your dialog box. Right? Take that again just for the purpose of clarity. I said click on the first point here. Then I moved in. I wanted to take the one in the middle, but when I move to the circle, it shows if I move away, it's off. So I will hold Control, right? I will hold Control and move in. The control allows that center point to be snapped and held. I can move in and then take that measurement. So now you could really see what that delta kind of measurement is doing. The first one is going straight, the second one from that straight point to the left, and the third one. So it's a 3D kind of measurement now. But what are we concerned with? The blue one, right? That's the one that is going what? On the vertical axis. So this measurement reading 2.098 is the reading that we require to know what, from the board to the highest component below. So I believe that is understood. I will just then head straight into what? My parameter section and begin to create parameters from these ones I've already read. You understand? That's why I had to show us that. I don't know if there's any question. I'll just quickly move. I'm about creating parameters now. Are we good? Is I need a response?
No questions, sir. You can go ahead.
All right, all right. So quickly create parameters. The first parameter I'll be creating, I will call this parameter my, top. You can't keep spaces, but you could use underscore. So I'll just say top, then I will say PCB offset. It's an offset, right? So I'll say top PCB was offset. The value we read was what? 34.599. Of course, it was in millimeter, right? So I could just maybe for purpose of clarity, decide to say, okay, an explanation for that. I could just say from what? Top surface. I won't do this again, but just so you could see how it's done for the first one. this commenting. So I'll just say from top surface of the PCB to the highest component. Upwards. Right? I could just leave it there. So what this is basically doing is someone can come in and really understand what those parameters are. So having done that, I'll just quickly create all the parameters at once, then we'll start designing. So my second parameter is bottom. So I just do underscore bottom PCB offset. Right? The value we just read now, what was that? 2.15. So I won't do a comment again to save our time. I'll click the next one, another parameter. Now, in Fusion 360, remember we're also going to be talking, during the course of the training, we are going to be talking about design for additive manufacturing. So you could take note of this second parameter, this third parameter I'm creating. When we get to the additive, proper, you could just see for yourself why we did that. But now you just know that, there's a parameter that is related to I'm creating that is as a result of, we trying to obey the rule of FDM, for instance, right? So I'll just quickly call this one clearance. I need a clearance, right? Oh, we are getting it. So I'll just call this clearance and then do FDM. So I'm being very specific now. You just look at it, okay, this was the one we used for that. So I will say 0.5, right? No commenting for now, I'll just leave that. Next one, another parameter I'm creating, I'll call it shell. I will shell, right? So I want to create a parameter for that. I will say maybe 2.2 millimeters. Let me even say 2. 2. Then we could say, okay, I'm not also commenting, or this one I could say, just for the purpose of clarity, I could say outer shell, right? Next parameter, which I'm going to create is my fillet. Take note of this. These things might look sometimes a little bit as if you're overdoing, but they could save you a whole lot of trouble when you want to debug or try to, make changes on your designs. You don't want a situation where you enter your design and you look at the parameters and you yourself, the designer, you are overwhelmed. It could happen. So I'm also creating one for my chamfer. So I'm also trying to show you that we can leverage parameters. Like we could call a parameter to be, to be tied to another parameter. So for instance, my fillet I have created, which is 4 mm. I want to use the same value for chamfer. So no need to create just number. I could just call the parameter called chamfer will be equal to fillet. I want to show you that that's possible. So you could just see. So yes, after the whole grammar, the important thing is the value is reading at this point is still 4. I hope we got that. So I'll create another parameter. I'll call this gap. We need a gap. I'll call this gap. And then this parameter will be 8 millimeters, right? So I'll create another parameter. We'll call this boss height. We need a boss. I'll show you how all of that works as we get there. So we'll just call this boss. I'll put H for height so that will save time. Right? So boss height would be 12, right? I'll create another parameter. We'll call it boss diameter. So BOSS, so my diameter immediately, and then assign the value to probably be 12 as well. Or I can also remember I could also say, since they are the same value, I can also say boss diameter is equal to boss height. You understand? Okay. So the next one I will do is to call another parameter. We still have another one called PCB thickness. Remember, we measured the thickness of the board itself. So that's this other one we are recording here. We had a number for that, which was 1.605, right? So I'll click on that, and probably one of our last parameter, I will say FDM, and I will say maybe H. Yeah. So I'll call this parameter 3 mm. Sorry, I'll assign the value 3 mm. So I am done with creating parameters, and I've shown us how to do this. Just to get a feedback that we are following, then I proceed. I'll click on OK. I'm done with my parameters. Are we good?
Yes, sir, we are good.
All right. All right. So now with created parameters, the first thing I will want to do is to have a plane. I talked about a plane earlier on, and I said you want to draw. You want to draw, but you have to draw on something. So assuming use your maybe lines, those things you're using to sketch as your pen or pencil, right? But you now need a place where you put those maybe should I say do your drawings on, for instance. So the how you can simply understand a plane is like your whiteboard or your drawing board. And the beauty of it is that you can orient the plane as you can position it in almost any way you want, 360, inclined, and so on and so forth. And however the plane is pointing at or is pointing to or is oriented, that is exactly how your sketch will behave. So your plane, that's more like saying the board you're using to draw, will influence how what you're drawing will come out. So I just wanted to put that one out. So a good practice will be you might want to avoid there's an origin here. Let me turn the PCB off for now. You will notice this origin plane here. This is the point where if you click on home, you see centralized on your screen. This is the point where your S axis, your Z axis, your Y axis are all 0. So they all read 0, 0, 0. Now, since you're trying to create the enclosure or design, which we have already created a component for. So the first thing you might want to do is to activate this enclosure, right? So you click on this radio button to activate this enclosure. Now, once you've done that, you can turn back on your PCB. Now, what do you notice is a little bit grayed out. You can still see it, but it's out. So that's one way you will know that you're doing it right. In the sense that now that I want to design something related to maybe enclosure design. So every other person, every other thing that is not related, does not have that relationship with the enclosure design, I would like foreigners, so they should be just there. Maybe we know they exist, but they should not disturb our work. You're trying to use some, kind of very basic terms to explain what is happening. So basically, your design file, your PCB design is grayed out to allow you continue working on your enclosure design while you're still seeing, in case you wanted to leverage, where is that hole again on the PCB? I don't know if you're getting me. Oh, where was that hole on the PCB? Oh, it was here. You can still see the PCB, but it does not have that direct relationship with the enclosure. So that's what's happening now. So what are we going to do? We can come over and put a plane, right? So we'll come over to where we have our planes. So these are all different tools that can allow you to play around with your plane, orient them in different positions, put planes on parts, on lines, on thin surfaces, and so on and so forth, right? So that will be your own, assignment to go and play around with most of them. We won't be able to cover everything, but we'll use as much as that concerns what we are working on. So the first one is offset plane. So all we are going to simply do is, okay, we are going to ask ourselves, where are we going to start drawing, right? Where are we going to start making this drawing? So since the PCB, we've already measured from under to the highest components under, and we've also measured from the top of the surface of the PCB to the top of the highest components on the PCB itself. So we could just start creating planes by saying, okay, offset plane, you pick on the offset plane command. Now you come over to the PCB, you tilt the PCB a little bit, come over to the PCB, and then you can click on this point. So what will you notice? The plane, more like my drawing board, is directly under the bottom surface of the PCB. The legs are still extruding, protruding rather. So what do? That means I will have to now use a parameter, that's one of those parameters we created to shift that plane. You understand? So remember there's a parameter we called the one we used to create from under the bottom of the PCB to the highest component, which if you click on this, you'll find out that was called bottom PCB offset, right? So I'll just come over, redo that command. Okay, sorry, it's still there. 1 minute, please. So this is the command we did. So we just right click on it, edit it, and then go over to the distance. So how far do we want the plane to be away from under our PCB? So I'll just put in that parameter we created, right, which is called bottom PCB offset. So can we see this? You can see it's directly on that word line. I'm zooming in so we can see where the plane is, right? Remember, we are trying to know where we want to start our design. That's to start sketching. But the truth is, if I still sketch on this point, it means that inside the enclosure, there will be a direct contact between the enclosure, that's the inner part of the enclosure, that's the plastic. There's going to be a direct contact between that plastic and this metal extension we are having here from the PCB file. And of course, that is not what's good. Both mechanically, electrically is very wrong. You don't want a situation where maybe even just placing your hand on something and you are already breaking something inside, right? Not to talk of the gap is not really there for air circulation and all those other things. So this will be a no. So that means that I have to do a plus. As I'm taking time to explain this, you now have to do what? A plus, right? So where I actually want my PCB, the inner surface of the enclosure, where I want it to start. Remember, I said we are going to have a bus, and we are going to see what a bus does and how it works. So we do plus, right? You hold shift, and then your normal way of inputting plus a positive sign. So plus, I will now call in another parameter we created earlier on, which is called what? Bus height. Are we together? So I'll click on that. So that means my future or my dialog bus, I have the PCB parameter and the parameter that was used in creating what the bus itself. So this is where I want, and then we are going to see how that will be of what advantage as we continue. So I'll click on OK. All right, so you can see a distance between the PCB and the plane. So for now, just for this moment, we could just right click on this plane directly and say create new sketch. Are we good? So you can see that Fusion has oriented the PCB for us. So you see this effect where when you want to draw, it does that reorientation. It's also something you could turn off in case it becomes a problem, because sometimes it can be very annoying. You understand? Okay. So now we have selected where we want to start our drawing. So the next thing I want to take note of is I want to take the boundaries of this PCB file so that I can start from there to now create what's my enclosure, to have some distance away from it, right? So to do that, I'll pick the offset command. Sorry, I'll do a projection rather. So I'll go over to create, I move over to project or include. See this command here called project. So the short form is P. So in case next time I will just click on P instead of moving that long journey. So you just click on that, and then it's a good practice for you to always project only the things that are probably required, instead of just projecting everything, because when there is time for edit, which definitely will come, that's when that's projecting both the ones that are required and the ones that are not required will become what? An issue. So in this sense, what am I going to do? I will just select just the edges, right? If you have an issue, you can just click on this cancel, you go back there. This is all I need, just these edges. If you notice, when I moved in, it was highlighting everything, meaning I can even project the transformer, the details of the transformer and everything. We don't really want all of that, right? So we just click this for now, click on this, click on this and this, right? I've mapped out that. Notice the projection link, this radio button. It means that this thing we have just projected will always be linked to the PCB. So if the PCB grows in size, maybe the electrical designer decides to increase the size of this PCB, this will also grow in size too, to accommodate what has grown in the parts of the PCB. There are cases where this can also be a challenge, depending on the kind of change that the electronics personnel have probably done. Like I said, some changes can be catastrophic, some of them can be mild. All right, so I'll just click on OK. And to just show us what we have just done, I will turn off the PCB. So this is what we have just done. I believe this is simple enough. We just have what? A line, right? We didn't have to create, we have to project. That's the difference. We did not start drawing, we just projected. So the next thing I'm going to do now is to do an offset of this line, right? Why am I offsetting? You don't want the PCB and the enclosure to have that friction, as if you're trying to force the PCB into the enclosure. You know, that kind of a thing where you're maybe trying to put on the shoes and your leg is probably not going in, and that kind of friction. That's not something you want for delicate parts like this. So that's why we have to do an offset before we start making what you start building. So for this offset, now remember when I called a parameter FDM clearance, if you can still recall, right? So this is where we call it in. Right? Just to zoom in to inspect if it's working how we want it. Now it seems to be going inside. Yes, it has done an offset, but it's going in, which is not what I want. I want it to go out. So I will do flip, right? Click on flip. So it's now outside. This blue one is the original line. The red one is one I've done an offset. So I'll click on that. So you just notice when you zoom in, you can see the one you projected, the purple line, and you can see the one we have just done. So having done this, please, before I do the next step, I would like to know that this is very clear, right? Feedback, please. Hello? Hello?
Sir, please, can you explain the fission part one more time, please? The offset.
The offset, are we having issues with the offset?
Yeah, just explain it.
Is it how I did it or why I did it? Because those are two different things.
It's more of how, but you could answer why before the how, so that we will know the reason why we are doing it, then we know how to do it.
All right, so I'll just undo. Control Z. I've done a Control Z. It's no longer there. But at least we got how we projected, right? Now, that's why I was using those examples. It's just to help us, picture these things, because most of the things you will get to really understand them when you see the stuff coming out, right? But picture this: you're trying to fit your legs into your shoes, and your leg is probably size 35, and the shoe is probably 34 or 32. You know what will happen now? Even if you're able to put that leg into that shoe, you know what will happen to that leg in terms of the pains you will bear, the friction. You could even damage the shoe, or even your leg. Something will be damaged either way, right? So that's the same thing. Remember, we projected from the PCB. This is the PCB. Let me turn it back on. Now you want to house the PCB. You don't want a situation where the thing you want to put the PCB inside, they are now having as if they are fighting, like there's friction, excessive friction between the PCB edge and the enclosure is going into. So that's why you need to keep an allowance, right? Now that allowance is the one we created as a parameter. I said clearance, and I said FDM. And I said when we get to maybe design rules of additive, we'll see how clearly how or why we selected 0.5. You understand? So that was why we did it, to have, so that we don't have friction between the inner wall of your enclosure and the external edge. That's the edge rather now of what your PCB. That is the why. Now the how is simply use what your modification tool called offset. I understand that some of us have not used CAD tool. I also understand that some of us have used. That's why I'm trying to balance, everything. So for those who have not used, you probably might not know how offset works. For those who have used, you understand how it works. So we are simply duplicating this line, but giving a distance. Do you understand? We are duplicating the same line, but giving what? With a given distance, rather. So you come over to this point. Now, all we've selected the command. All it's just asking you is select what you want to offset. So that's what I'm just clicking this one, this, and this. Now I said, although it has corrected now, initially this is how it was. It did an offset. So I said duplicate. Yes, the line has been duplicated, but it is going in, which is even a problem. This is what I mean. If you turn on the PCB, The PCB is on now. Can you see where the PCB moves around? This is the edge of the PCB. Your line you want to keep as allowance is even going inside. So that is what's even more disaster. You would have even left it where it was without offsetting. So that's why I had to do a flip. Right? Click on the flip. You see it going out. So this is your PCB. Now, do you see the PCB where it ends? Now, this is the space that you have kept. Now, for the magnitude, I said we created a parameter called clearance. So I will just put that in. That's what I did here. Remember, we were creating parameters before, so we already know where the parameter is coming from. So I just used it. That's all I'm saying. If sometimes you want to know what it is, you're not saying you click on the f of x, and there you just see the value will be reviewed. You understand? But it's not the same thing as just putting 0.5. There are two different things. So you click on OK. That is the how I did it. I believe that's understood. I want to move to the next one. Are we good?
Yes, sir. You can move on, sir.
All right. Thank you so much. So the next thing I'm going to do is now I want to add form. Remember how I started with some very funny terms. I said the cell, the sketch. Now maybe the muscle or the tissue, the body, right? So we have done a sketch, a skeletal system of probably the geometry of what the enclosure should look like. But now we need to add life, right? We need to add some form to it, right? In this case, since we are not working with surfacing, we are not trying to sculpt, we are not trying to, go all, that route. That's a different workflow. We also want to add, make it have a solid form. So remember, we're on a sketch mode. It will also be good practice for you to just, okay, once you're done sketching, you click on what, finish your sketch. You understand? Now, another good practice would be you come over to this and then do a proper naming convention. This is the very first sketch that I will be building a lot of things under. So automatically this becomes what, my base sketch. So I will just click on this and rename. I will call this what, base sketch. So each time, whenever I want to troubleshoot or see what's happening, me looking at that guy, I know who and what it's doing. So this is a good practice. I'll call this base sketch, right? Okay. So this is our sketch now. We want to add form to it. The reason why I'm taking time is because what I want to do next will probably need you doing some imagination. So I don't even like this origin here. So I'll just turn everything off so that we can just see just the lines. Right? So we just have these two lines. So now add form is a very simple way. You just come over and extrude is one way you can get that done. All of these tools here, you see these tools, Fusion has a workflow from left to right. So even those things you're thinking about to do, first of all, you must create something, then you have to modify the thing to look like what you want. Then when you're done, probably you have to assemble them and then start pushing. That's why you're seeing it arranged this way. So even the sketch, if you see, it's still part of Create because you created sketch first before extruding. So please take note of the shortcut E. So next time, we might just click on E on the keyboard to activate that command. So I'll click on Extrude, click on this. I zoom in to be sure because it could be tricky sometimes, just like we've seen. You selected one part, the other part is there. So I'll still click this as well. If you're having issues on selection, one of the easiest ways is what? You hold Control and move in. If it's still not working, it means there's probably a broken link, right? So if there is a broken link, you have to zoom in and check for instance, if there is a discontinuity in this line from this point to this point, this place will not be selected because it's not enclosed. That's how the extrude works. It needs that enclosed what? Region. Are we together? So I've selected this, right? If I pull up, you will see some solid form added. I just want to show us how it is. But we need to, we cannot do guesswork. We need to, it has to be defined. There's a reason why it must be 55 or 67. Are we together? So for us to get it right, you simply move on to, excuse me, please. All right, sorry about that. Okay, sorry about that. So, like I said, you have to be you have to be very intentional about what the size and everything. So for us to get it right, all we are simply going to do is we could turn on the PCB for now. We are not seeing it, right? Because we have covered it with this block we just created, right? It's understood why it's behaving that way. So I could say, let's have a wireframe view, or maybe a more skeletal view, so that we can actually see what is happening in real time. So you come over to display, you switch to wireframe. What I've just done, this long process, you can simply do it by hitting Control on your keyboard and playing around with your 4, 5, 6, 7. So this is what I mean. If I click Control 4, you can see what's happening there. Control 5, you can see what's happening. 6. Let me pull this out again. Sorry, a minute. Let me just click OK just to show us. So you hold Control 4. You can see it has a very smooth texture. 5. You're able to see there are hidden lines now, which are visible to you. You just play around 6, then 7, and so on. So we will be using this wireframe so that we can see the see in real time whether we exceed the components. But of course, we also do that mathematically as well. So remember, I created I used the extrude future. Take note that these things we are applying from these tabs, right? They are called futures. You will see why, and why I emphasize this, because when I'm selecting, I have to select, oh, I want it to be a future or something in the nearest maybe in the nearest steps we are going to do. So I selected a feature called extrude. This is it on the timeline. It's here because I selected OK. So I will right click on it to edit because we are not done. We've not finished what we are doing. So I'll edit the future, right? We are back to our dialog box the way we saw it. So now what are we going to do? Since the enclosure is starting from the bottom, right? So let's just bring it back to, we'll zero everything. We'll say 0. So we know where it is. This is where we started drawing, right? Please pay attention. This is where we started drawing. Next thing I will do, remember our parameters. This first one was from, there's a parameter we created that we use in moving our sketch down to this point. Are we together? So we can basically just quickly check what that would be. So that was when we did this you could see the plane here when we created this plane. So if you edit that feature, you see this guy. This is what we use in moving the plane down. Bottom, PCB, blah blah blah. Is stored under D18. D18. If you also come over to your f of x, that's where you see your parameters. Of course, you won't see them here because these are user parameters. So like I mentioned to us that you will find those things that are consumed by the design inside model parameters. So you come over to a model parameter, go over to plane because we did it on the plane. This is it. This is that guy you just saw, D18. Are we together? So I will just call this directly and use it for what I want to do. I believe we've gotten that aspect. So going back to edit the dimension. So I'll say 0, 0, everything. So we are back to where it was before, right? So it means that if I should do D18, if I should write D18, are we seeing what's happening? It has moved, but it's moving in the opposite direction. So I will use a sign convention to change it to what I want. So I can use parentheses now and just come over to say, move over to this end, since there will be many. I will do open brackets, put the negative sign there, right? It's still showing red because I've not closed. I'll close the bracket. It's up now. I believe we've gotten the first one. So what I've just done, I've added form. Remember, this is going to be a block, but I kept it in this view so that we can see what's happening. When we are done, we'll have a full block. So we've added form, and that form has just started from here and has ended directly under the board. So what does that tell you? If I want to reach this top, I need to keep traveling, right? So we say plus. That's what I meant by traveling. I want to add the next one. There's another parameter we created, which was the parameter that was guiding the PC. That's the parameter, sorry, we created for the PCB thickness. Are we together? So simply, even if I've forgotten, I could just try to play around to see if I can remember. So PCB pops up, I will put it there. Right? It's also going down because what? Of sign convention. So we'll also do this. Open brackets, put the negative sign there. Close that bracket. If you could notice, look at where it is now. Look at where our form is now. It's going up, right? Taking time so that maybe I don't have to, explain it too many times, right? So we'll go. We still need to keep traveling. So I'll say plus again. since we have seen the behavior, we just open the bracket at once and know that whatever we want to put, we'll add minus in front, right? So the next one would be from this point, there's another parameter we created. That was the one we measured. We say from PC, the top surface of the PCB to the highest point. So what do? I simply come over to my dialog box. I move over to the next place. That guy must have forgotten the name, but we can just start searching. We could say top T, something comes out. So just right there. I'll put that in and then close that bracket. It's going down as well. You know the reason. So we'll do what? Add the minus. So can we see where we have arrived? We are now up here, right? We have traveled in, we are adding form as a solid form. We are now at the tip of the transformer. But again, the enclosure cannot have direct impact with, especially the electronic component, which we know are delicate, can electrocute. A lot of things can go wrong, right? So that is where that guy I brought in called gap. We created a parameter called gap. I made it very clear. So we just know it's just gap, nothing else, just to have what the space. So you see the parameter here. It's still going down. You know the reason why, sign convention. So I will open up another bracket, put minus, go back, close, and that's what's happening there. Now this is the place where you will now start having. Remember, they say the enclosure during this specification should not exceed so and so. So now I'm putting gap is equal to whatever value I use for gap, and this is where it is. If after measuring this thing, this thickness, that's the overall thickness, has exceeded what I was given as a limit, it therefore means I have to now reduce the parameter, the magnitude of what gap is. So this is what I'm saying. I'll just click on this guy, click on OK to accept it first of all. So I'll bring it back to the normal view. Like I said, you will do what? Hold Control and activate Control 6. Or if you don't want to, you can start traveling around and looking for it on your visual style, right? So this is what we have just done. The PCB is required what right inside. This is what I'm saying now. If you should measure this, I for inspect, remember I told us now. By now we've gotten most of it. So just click on I on your keyboard, you pop this up, and then you can take that measurement. So this is what we have, right? So this value has exceeded. What do we do? Remember that as long as, let me turn this off, turn off the body and turn on the PCB. As long as this PCB is from this point to this point, is not under our own control. That is how high it is already, right? The only one we have control is from this point to this point that the PCB have is the length of that PCB. That's the entire assembly. The one we are building now, we have control over the one we are building, but not what it came with. So what I'm trying to say is you could just come over to this point, turn that back on. And at this point, maybe you might also want to have some ways to see what's happening without using those Control 6 and 7. So you can just run it over to inspect, click on sectional tool, and then you can select this space as your section, just like you do in the engine drawing or related courses. So we just have a sectional view of what's happening there. Of course, you can see that the PCB is buried, and it's because this is a solid form. There's no vacuum, right? So I'll just keep that in there. Now, what we have just done is recorded here. I have to show us that because we might be using it from time to time as what section, what analysis. So I could just decide to call this maybe right. It's still section analysis, but so I could know that, okay, this one will give me leverage to see what's happening on the right. I believe we are good, right? So I will turn this off for now. And then the next thing we probably want to do, since we've extruded, we probably want to do what? A filleting with chamfer, and then we shell. Now take note of how I'm going about it. Filleting, chamfering, chamfering rather, or chamfer, fillet, then we shell. Now the first two, the chamfering and the filleting, is related to the additive manufacturing we talked about, right? The reason why I'm bringing it in. Are we good? Now, the one that has to do with the shelling coming later now has to do with what? You being able to achieve your end goal right in this workspace. If you shell first and then try to apply the fillets and the chamfering. You will be eating up the material, and you will not be able to achieve, what you're looking for. So this is it. We just see it. Just had to explain, but we'll see how it's done. So now we have this enclosure. We'll turn off the PCB, so we'll be sure that we have just this. And take note, once we've created something like this, where you have a solid form, it's now recorded. It's still under component enclosure, but it's recorded as a body 2. You could see, right? And the reason is because this file is not yet a component. This design you're seeing, this data is not yet a component. It's just a body. Like multiple bodies come together, they make a component. That's how it works, right? So I will just apply my chamfer. Don't know, maybe if there's any question, we could just quickly, before I proceed, please. So I'll be sure we are on the same page. You have a question?
Okay, sir, we just have just many questions. Is the clearance gap, was it among the specification you did during the parameters, or those things were added for this one? Was it among those things?
You mean on the slide or in the design? I don't get you. Or on the parameter section itself, this one?
Yes, did he add a clearance gap for the?
Yes, this is gap. It's a parameter on this one, 8 mm. And then the one for clearance.
Okay, there's a specification for clearance.
Yes, now I mentioned this one and I wrote FDM so that you take note of it. I will still talk about it when we are talking about additive manufacturing.
Then there's another one for gap. There's gap here now. Yeah.
This one is you're the one using this, and then you'll be able to judge if it's okay or less depending on the specification. Remember, we had the specification.
Yeah, and the project requirement that you raised.
Yes.
How did you bring out this parameter dialog, please?
The dialog box.
Yes, sir.
You just go over to you find them so many places under modify. Mine is here because I kept it here. Under modify, you see it here, right? I pinned mine. This is where you pin them. If you click on this, it goes off. So because I use it a lot, in fact, it's more like my life when it has to do with fusion. So I click and pinned it to my workspace. Are we together? So there are many places. Okay.
That is it. That FX you click. You pin
yes,
it
FX.
To.
Yes.
Okay. Thank you very much, sir. Maybe at the end of this section we'll have our own questions and contribution.
No so I can proceed.
Yes, sir. Thank you.
All right. So now we have done the extrusion. So we'll quickly add the chamfering. I mentioned those two being related to additive, and we'll see how when the time comes. That will be probably tomorrow. And I mentioned the shelling coming after as a result of you being able to achieve your goal. It's quite important because there are times when you have to now start, fighting with it if you're not really conversant with how it works. So I'll just click on chamfer, and all I want to chamfer is just these two. And because already I'm thinking in my head, we are going to 3D print, right? And for it to come out in a certain way, there are certain things I need to certain rules I must obey. And one of those rules, like I said, we mentioned it, we are going to bring it back tomorrow. But let me just so that you start now to have it already in your head, is that the point that is going to be printed, that is going to have contact with the bed of your printer, or should have a certain level of chamfering or filleting. Want to maybe enable you being able to remove the product from the bed without damaging the product itself. That's one. Second one could be as a result of, okay, you don't want during the printing, there are certain failures that come in. You understand? As a result of, you are not having that part, have that form, maybe slanted, because that's what the chamfer is going to do now. And then you're going to add your filleting, probably because you want it to also be smooth at the end of the day. Because, for instance, okay, let me just, we've selected chamfer. You saw where I got it from. Is one of the modified feature. You pick it up, you come over to the edges, you select the edge. Take note, I didn't select the entire face. I just selected the edges. And then you want to give it a value. So remember, there was a parameter called chamfer. So I'll call that parameter in C, right? You can see it's already popping up. So I'll just select that, right? So you can see what it's doing to the enclosure itself. So if you keep it here, It could also have its own, downsides, being that maybe it's going to be too sharp or not really looking pleasing to the eyes and stuff like that. Don't forget you have to be well balanced. You're balancing both beauty, functionality, everything all in one during your design, right? So you select OK. A quick one, you could just do maybe your Control 5. Sorry. Okay. Control 7 rather. Then click on the PCB, turn it on to see if you're on track. Because there are cases where you will chamfer. Like I said, if you watch what is happening here, if you look at it in this more like a 2D form now, like a line representation, you can find out that this part of the material has been eaten up. And there are cases where these components can come all the way here, and you don't want it to maybe eat up and then expose the component. But in this, with this particular design, we don't have such issues because the highest component is just sitting somewhere inside and doesn't really have that direct contact with it. So we are good. I'll click to return it back to the view we had before, which was the this other view. So the next thing, I will use the fillet to just, like I said, beauty, right? Make it smooth, have a smooth transition. That will also help us because there's something called stress concentration. All of this we will also get to know tomorrow, the additive aspect. But you also help to disseminate distribute that stress instead of allowing it being concentrated. Because if you could recall from maybe your engineering practice or maybe science, the knowledge of science and all of that, you take notes. You must have heard, that the points where you have like joints is always usually the weakest point or the weakest maybe member. You understand? So places like that, maybe you have two walls coming together. At that point where you have the joint, you're having them join together. That is the weakest point. That's the point you could that a failure could occur rapidly. So one of the ways to handle this is how we call in fillet. That's why we call in the fillet command. It helps you distribute that stress and to make sure that you're not having one place. Just maybe you just press a side and the thing just breaks into two or cracks or something like that. So it's also not just helping you make it look smooth, not just for beauty. It's also having a natural, functional purpose. So you click on that and we click on fillet. Fillet is also a parameter we created. So I'll call it in FI. You can see, click on fillet. Can you see what's happening now? I believe between this one and the other one, you probably would desire this more, right? So I'll click on this and click on OK. So I believe there is no other question because the next thing we are going to do now is to apply the shelling. So I'll just apply the shelling. When I'm done, I will make room for if there's any question, then we could proceed. So this is how the enclosure is. Remember, we had a knife. That's what I mean by that. Our section tool that can allow us to see what's happening inside. So if you activate that, it has turned it on, you can see what's happening. This is basically how the entire enclosure looks without being cut or anything, right? Zoom in to see that everything is nice. Okay. So the next thing we are going to do, I'll turn that off, is to apply a shell. And just to be on the safe side, I'll turn off the PCB so that nobody gets damaged during the process. So I'll turn on the PCB and ensure that this is the only components active on my screen. So because I want to shell uniformly, right, I will select the entire body. And then when I apply, remember shell has a parameter as well, which we created. So we'll call it in shell. But take note, this is showing us inside, meaning that after excavating the materials, this is how the shell works. It's going to remove materials and then remain the magnitude that you have stipulated. So if you say shell, maybe this bottle for me, it's going to remove all the materials within and then remain a wall thickness of, let's say, if you say 2, that means after removing the material, what will remaining will be what? 2 mm. But what why I had to mention this is that this can be both inside and outside, or even was symmetric, which are the things you're seeing here, direction. So if I am shelling inside, I will just click on this, okay. So remember, with this one is inside now. Now look at what happens. Look at what happens. I will turn this on. Can we see what's happening? Material has been removed, and we are now we only have a wall remaining now. But turn on the PCB. Can you notice? Can you see the clash between the PCB and the wall? So this is why you need to take note of these things. You've done the right thing, but you just did it the wrong way. You did the shelling, that's correct, but the wrong direction. So now it's clashing with the wall, which you have taken time to add clearance. See how that makes that one step makes your work what difficult, right? So to correct this, I have to do this on purpose. So you just see our edit and say what shell outwardly. That's outside, right? Calling the parameter again, shell. Enter. Already we can already see what's happening even without me saying much, right? I'll click on OK. So what basically happened is that all those things I was setting up during the time we were designing, it's respect that. So that one will become my inner wall, right? And the shelling now is happening outward. So it's still removing material and remaining a wall, but it's doing it in the negative direction. That's the outside direction. You understand? If you check this wall, it's still going to be whatever I set as my wall thickness, maybe 2 mm. So this wall will still be 2 mm, but respecting that I had kept a clearance here. So I will pause here for questions before we move on to the next one, please. Any questions? Any questions?
How did you correct? Sorry, can you come again with how you corrected that clearance distance that was touching the PCB that time? Like after we've successfully done the added clearance to it, but then you did something and it covered it. How did you correct it?
Okay, are we having issues? Is it the general house or just a few persons?
Just a few persons. Like, how did you correct
All right. Okay, please. Thank you very much for the question. Just to help us, we don't have much time. So we'll try and kind of concentrate so that because I actually spent time to explain and to also do so that you see how it's done. You understand? I understand that some person might not get it immediately, but I believe if we pay more attention, we'll be able to see this because I'm using very quite basic terms, right? So this is what I did. I will undo. So you even see, I will click on Ctrl Z, right? So this is how it was. Clashing the wall. So all I said was just go back to the shell, right click, edit. Now instead of inside, you do outside. And then you put your same parameter. That's what I just did. You understand? Select, and that corrects it. Right? I hope that's gotten now.
Sorry, just one more time.
We still did not get it.
Yeah, the signal was.
Okay, I will undo again. Undo. This is how it was. So it's a future shell. I remember what I said. I said all of these, they are all futures, all of, as you see them list. You understand? So the future I applied called shell from the modify tab. See the future here. It is now on my timeline. I don't need to add another one. I just go back to that one and edit. So edit future. Are we together? Change direction outside. That's from inside. You select it should be shelling outward now, not inside. Then you put the value. You call it what? Shell. Why am I calling it shell? Remember, we created a parameter called shell. If you're still in doubt, it has a number. If you click on f of x, you see the number 2. Right? It has reviewed. So you click on it. Is this gotten now? Do we get this now?
Yeah, yes, sir, we got it.
All right, please help me help ourselves. We don't have much time, so let's just try and be more concentrate a little bit more.
The reason was that the cable was glitching, so at some point when you were saying something, so we couldn't grab exactly what you're saying.
All right. So for us to be able to cover up, I will start now to prepare our minds. We probably might go to 30 instead of 2. We all know the reason why. I'm just trying to so that we don't have too many things being carried over. I believe you understand what that term means. So we might just have to stay to 2:30 probably so we can cover something, please. All right. I believe that's okay. Feedback, please.
Yeah, that's right.
Solo, Solo, are you on the call? I'm not hearing him again.
I'm here with you on the call.
All right, please help me do the timing, please, so I don't get carried away.
So,
okay.
How many minutes more, sir?
We know normally we're supposed to stop by 2:30, but I'm saying we have to extend to 2. Sorry, by 2. We're supposed to stop by 2. And so we'll have to probably extend to 2:30 so we can cover something tangible.
No problem.
All right. Okay, so thank you for that. So what are we do now? The next thing is this: we can still continue work. You know, it might not really. People will have their different ways of going about design, and I want to also make you have this in mind. This is not the only way you can produce this. There are many ways you could get this out. But the important thing will be which one of them is best suited for what you're working on. In case, because there definitely will be that in case where you need to make changes. You understand? When you start practicing, you understand, how you could just be like, oh, can we change this? Can we change that? Can we do this? Can we make it smaller, shorter, and so on and so forth? So you don't want any what we call workflow now. That when you remove the pin, just one pin, the entire house falls on the floor. I don't know if you understand what I'm trying to say there. So there are many ways, but there are also best ways. So you look out for those best ways. I don't expect you to get everything immediately, but with time, it's definitely going to be clear. So what I'm trying to say, why I had to go that part is I could still continue this design as it is and still get everything I want. But that will probably not make sense for us, especially since we are trying to grasp how to get certain things done. So instead of us to continue on this design, like adding more things, the first thing would be for us to open up this enclosure. So instead of having it, remember it's still full. And that's why I'm still probably using analysis, trying to section it. But this enclosure is still closed. So what will be best at this point, and for our audience, will be to split this into 2, so that we can see what's happening inside, and that's we can have a top and a bottom. That's basically what I'm saying. So for us to do that, what do we need? We need a knife, and then the command. Our knife is the plane. I'm using this term so that we can always, these things can always stick. We need a plane, which is going to be our split plane, and then we need the split command itself. This is the split command sitting right there looking at us. You go to modify, in case you don't see it, you find it here. We could split faces, we could split bodies, we could even use silhouette split. But of course, as you see them arranged, that's also like in order of importance and in order of level of advancement. You probably don't want to use a silhouette split when you don't really even understand how a split works, or even how a split face works. You understand? But they are not, I don't mean to scare anyone. They are not as if they are too complex, but I believe if you should even understand how the split works, then you could move over to other ones as well. So we need a plane, like I said. So what do? I'll come in here to create a plane. I could basically just offset a plane from the surface. So there's one good thing about Fusion and some other parametric design softwares. And that good thing is the fact that apart from using a plane to draw, which is like saying using a plane to have your sketch geometry, you could also use the model itself. That's the model geometry to also do your sketching. What does that English mean? You could sketch directly on the face, and that face will act as your plane. Of course, there are consequences. All right. So you come over to this point. For this one, we don't have much, things to be afraid of, because it's just a plane and we can control it. Now we have this yellow sign. It's telling me that the plane I am about to create will not be seen. What's the reason? Let's run over to our browser. We come over to our browser. What's happening? It is a construction tool. Can you see? I picked it from here, construct. And Fusion records that everything I'm picking here to work on under what is called construction as a folder. So construction is turned off. You can see the eye is off. So it's telling me that I can't see it, and that is true. I can't see it because it's off. So if I should turn this on, you can see it's now